So, good morning, everyone. Welcome to this new AJS. In the AJS of today, the speaker comes from the Sorbonne University of Paris. He is a postdoc and he works on machine learning, turbulent modeling, and really other models for fluid dynamics. He is Mourad Oulghelou. Sorry for the pronunciation.
That's all right.
Thank you for the invitation. And the talk of today is entitled Machine Learning Assisted Blending of Data-Driven Turbulence Models. So the stage is yours.
Thank you very much, Nicola. I thank Nicola and Guglielmo for their invitation to present my work on machine learning assisted blending of data-driven turbulence models. So this presentation will be like a summary of a paper that we have worked on lately on blending expert models to produce models that are Rand's models that are augmented, but in an efficient way. So let me give you some context and motivation for the work. So Rand's-based turbulence modeling. So these such methods are used widely in industry and in many applications for their costs. However, in considering, for example, the K omega SST model, we rely on the linear eddy viscosity hypothesis, which is a basic hypothesis, and sometimes it fails in many cases like non-equilibrium turbulence, separation, strong adverse pressure gradient, 3D effects, shocks, etc. So what we are proposing, we have proposed in this context is to use some high fidelity data that are available to correct these models. So before our work, there were works that proposed some expert models that work good for some phenomenon, like for example for separate models, or for jet models, etc. So what we propose here is a mixture of these experts in a dynamical way. So the goal of this work is so here you have the paper. If you are interested, I invite you to go check it in the code. So the goal is to combine multiple data-driven neurons corrections, as I mentioned earlier, which we call experts. And exactly, we have three experts. We have the baseline model that is good for attached flows. We have a model for separated flows, and we have a model for the jet. So these models are used to be blended intrusively in the Rand's equations in a fashion, in a way that preserves the structure of the equations. So as outline of this presentation is to give the data-driven augmentation strategy of Rand's model by adding two terms, which are an extra anisotropy tensor and a turbulence kinetic energy correction. And then to show you the machine learning procedure that we have used here is to construct some weights to give importance of each model based on some physical features. And these weights, this mapping between physical features and weights is learned by using a random forest regressor. So once we have done this on some trained flows, here the training flows are chosen to be the channel flow, for which the baseline model is good, and the separated flows, which are the conversion diversion, the curved backward facing step, and the periodic hill, and a near sonic jet flow at the end. And once done, the training on these flows, we apply our methodology of blending to three new flows that were not part of the training data, which are the flat plate or the and the wall-mounted hump and the NACA 0012 at variable angle of attacks. So, as all of you know, these are the equations for the RANS model, and we have in the baseline RANS hypothesis to consider the Reynolds tensor to be in this form. So what we propose here is to add a correction, which we denote here by delta for the Reynolds tensor as an extra anisotropy term. And by adding this term, we have a term that is added also to the turbulent kinetic energy that we note hereafter by RK. All right. So the idea here hereafter is to know how to learn this term for each case depending on the flow features. So here I just wanted to show you how the term RK manifests in the equations of K and omega, and the turbulent and nu t remains unchanged. Okay, so the hypothesis is to use the pop basis in order to construct the B delta and the RK. So the RK, we made here an hypothesis that it is a contraction between this tensor that is constructed from this basis of pop and the gradient of the mean velocities. So here, these bases can be constructed from the main velocities, and these weights are to be learned depending on the case. So what we use to learn these weights, we use the symbolic regression method, which is called also SBL Sparta. You can check the reference of shear here. And we learn these weights to be a bivariate polynomial of degree 4 of depending on the two invariants, here mentioned. Okay. So just let me give you a quick recap on the SPL strategy. So I will briefly, first of all, let's assume that a model, so here you have the design matrix that I denoted as B here. It's composed of all these terms, the combination of these tensors with the hypothesis of that I mentioned here, that alpha n delta, and alpha n r are polynomial in terms of the invariance. So you will have here combination of these terms with the monomials in function of I1 and I2. So these are all encompassed in this matrix B. So here we assume a standard linear model where the observed data vector y is modeled as a linear combination of basis functions that are, as I said, encompassed in B. Here, weighted by coefficients vector that I denoted here by W, plus a Gaussian noise with standard, plus a Gaussian noise here epsilon with mean with 0 mean and standard variation sigma square. So here we use the SPL prior is as given here below, and we place a sparsity promoting prior on the weights omega or W. Each weight is assumed to follow a 0 mean Gaussian distribution, which is with its own precision parameter alpha. So here we try. The key idea is to maximize the evidence, and we iterative we do this iterative procedure and pruning unneeded weights by using this hyperparameter which controls the shrinkage. Okay, so here are the flows that are used for the data that are used for the training. So we have the channel flow, for which we used the RANS data, as we know that the RANS model is very good for this flow. For the near sonic axisymmetric jet, we used PIV data from Bridges and Wernet, and we used three sets of data for the three separated flows, as mentioned here, LES, DNS, and ALS. So the learned model that we have used are mentioned here. So we have the baseline model with zero correction, with no correction. You have the jet model discovered by the SBL Sparta here, which involves only the first tensor. And you have the separated model used here, which involves here a correction on the momentum equation with the second tensor and the correction in the turbulent kinetic energy in the first tensor. So here, let me recap what I just said. So we have three models that are discovered that we denote here MSST for no correction, MSET for the separation correction flow, and M axisymmetric near sonic jet for the jet correction. And the BIG delta was expressed as a function of the tensors here and the invariants. And as I said, for the correction in the turbulent kinetic energy, we have it as a contraction between the tensor that we have formed from these bases and the gradient of velocity. So by using all this, we have learned the coefficients alpha n and alpha n delta and alpha delta and alpha r from DNS, LES, and even PIV data. So the strategy that we propose here is to use a blending strategy between models. We suppose that these models are denoted by calligraphic M here, and we try to build a blending of this correction using the correction of each model, using some weights here that needs to be calculated and learned. So the idea here is we know to calculate this for each correction, for each model, but we don't know how to calculate these weights, but we need to discover them. So we need now to determine what are these weights. What we have done is to, because for the training flows, we have the high fidelity data. So we built the weights using the horizontal velocity by using a Gaussian function like this. And we tuned the sigma such that the chosen sigma represents the best fit between the reconstruction of this using weights and like the reconstruction of the high fidelity velocity and the weighted velocities from each model. Now for the training data we know how to calculate these weights, but for extrapolation cases we need to discover them. So what we have done, we have used a set of physical features that are denoted here as eta, and map them to these weights using a random forest regressor. So these physical features were chosen from the set of the paper of Ling and al. As follows. These can be constructed from the mean velocities and the strain and the rotation tensors. So the idea is as follows. So we collect, for the training cases, we collect the physical features and the weight that we have calculated using the Gaussian function. And we fit the random forest regressor that best reproduces the exact weights. So for the deployment for new cases, we have the following. We do the following. For a new case, we calculate the baseline K omega SST model. We extract the physical feature, and by using the physical feature, we use the random forest to predict the weights. Once we have the weights, we can build the blended correction of the momentum equation and in the turbulent kinetic energy equations. So here on the training data, we have tried to inspect how our random forest performs. So here you have the exact weights as function of the random forest weights. So we checked that our random forest predicts well the weights starting from the physical feature. We did this in a training set because we have divided our set in 80% of training and 20% of test. And we saw that our random forest regressor can be trustworthy. So can be now trusted to be deployed in unseen cases. So let me now start by some results on the training flows. So the first training flow was the channel flow. So here I have represented the velocity profiles, and you have here the errors of each model. So for the first three, for this case, the baseline model is expected to perform well here. And the jet model was the worst, followed by the separated model, which is not that good for this case. But what we can now conclude from this test is that our blending strategy like detected that the best model. I mean it gave more weights to the baseline model, and it ended up with an error which is similar to the SST model. Now for the second training case, which is the axisymmetric near-sonic jet flow. Here you have the velocity profiles at many locations, and here you have the weight distributions in these location. Also, you have the velocity here along the axis and the corresponding weight. So we know that for this example, the jet model is the best model that performs well. So we are expected that our blending strategy tries to profit from this model and give it the most weight in order to give a good result based only on the data that we have. So this is the case because when we see here, for example, in the weights, we see that the weights predicted by the random forest give here in red, you have in red the jet weight, which are the dominant weight here. And you have here followed by the SST, and in last position, the separation weight in blue. So this confirms the good behavior of our blending strategy, even though the blended solution was not as good as the expert model, but it succeeded to automatically select like a compromise between the three models and avoid the worst performing models. So even it is situated between the jet and the SST model, it remains a good prediction, and the error is acceptable. Now let's move to the third class of training flows, which are separated flows. And here I show you for the periodic hills and the conversion diversion flows, the velocity profiles at some locations with their corresponding weights. So here in these cases, we expect that the separation model performs well, which is the case that can be seen here in the weights. We have the weights in blue, which are for the separated model that are dominant, followed by the SST model. And in last position, we have the jet model, which is not relevant in this case, as can be seen in the prediction of the expert INSG model. In terms of friction and the separation bubble, we can see here, I can show you here the table of prediction. You see that the shading color means that when we have a color that is close to gray, it means that the error is big, and when it is light, it means that the error is low. So you have here the blending model, which gives good predictions for the velocity and for the friction. And also we have inspected the separation bubble length. We see that overall the blending model here performs very well for the three cases of training flow. All right, now let's move to the first test case, which was not part of our training set of data, which is the zero pressure gradient boundary layer flow. So here we see that by deploying our strategy of blending, we see that the blending strategy, of course, here before going to the blending model results, of course, here I should mention that the omega SST model is the best performing model. It is expected to be the best one. And here you can see, for example, for the friction coefficient and for the horizontal velocity, that the blending strategy takes advantage of the good behavior of the omega SST model. And even though it goes here between the two, but it's still acceptable because it is an automatic way to choose which model will be good in which region of the flow. And you can see here, I have plotted here also the weights in the profile and also in the wall. And you can see that the two models that are competing in this case are the SST model and the separation model. In contrary, for the jet model, which is not relevant in this case, we have very low weights given by predicted by the random forest strategy. And overall here, the results are very acceptable and showed that the blending model is still performing well and predicts automatically good results. The second test case here is the wall-mounted hump, which is supposed to be a separation case. So here you have the horizontal velocities and also the weights. So as expected, in blue, you have the separated model, which takes more weights, which is a good thing. And we can say that our mapping features weights works well. And we see here also that we have good predictions of overall in the overall domain of the velocity and also of the friction and pressure coefficients by the blended strategy. Now let's inspect the separation bubble, and we can see that the blending strategy here predicts very well the length of the bubble, and also the starting and ending point with respect to the experimental results. So if you can see here, you have in blue the separation model, which predicts a smaller bubble. So the reattachment point is earlier than the experiment, and you have here in green the SST model, which overpredicts a little bit the bubble, and of course the jet model, which is not relevant in this case, which overpredicts obviously the bubble. So the blending strategy here comes between the two and take advantage of the two features of the separated model and the SST model, and gives a good prediction of the bubble length. All right, now the last test case here is the NACA 0012 with the variable angles of attacks. We have done the experiment with the three expert models, and also with the blended model. So we have here plotted, for example, in this figure, you have the drag and with respect to the angle of attack, and you have the lift with respect to the angle of attack. We see that the first these figures are the same of this with these figures. We just omitted the results from the jet model, because they do not let us see what happens exactly in the results. So you can see here that the jet model is not very good overall. So let's now inspect the two models that are competing in this case, which are in blue here you have the separated flows models, and the baseline model SST. So the blending, you can see that the blending model takes advantage of the two and gives good predictions with respect to the experimental results. And also this can be also seen in the lift coefficients as well as in the drag coefficients. Yes, so here just a complementary example to show you the pressure coefficients. We can see that, for example, here for the angle of attacks, so we have the pressure coefficients and also the friction. So for the pressure coefficient, we see that the jet model is not performing very good in the case of the NACA 0012, and that the two competing models, of course, are the blue one and the green one, which are the separated models, separated flows model, and the baseline model. And we see that the blended model in orange always gives a compromise between these two and gives good results automatically without knowing priorly that in this case a model is well performing or not. And this can be also seen in the weights distribution. In the upper wall, you have here the two models that are competing, and the jet model, which takes low weights, and which means that is not very relevant in this case. So I finished my presentation, and I will just give you the conclusion of what I just presented here. So we have introduced the blended approach, which consists in a mixture of specialized transcorrections. Here in our case, we have three corrections. So the no correction model, which is the SST model, and the separated model, the separated flows model, and the jet model. So we use this intrusive strategy is consistent because we apply corrections within the PDE, within the RANS model. So we don't have any inconsistency in terms of conservation laws. And the weights, how we predict the how we predict these corrections, we use some weights that are found via the random forest on some physical features that are mapped directly to these weights. And so the observed gains is that we had observed a good performance on the many physics that appears in the flows with an automatic selection of the best model that performs well with respect to the physical features that we have presented. And the generalization on test cases that were not part of the training test cases were good, as we have seen in the zero pressure gradient boundary layer example, for which the SST model is known to perform well, and the blended model gives results that are close. And for this case of the wall-mounted hump, for which we know that the separated model is expected to perform well, and that the blended model gave a very good compromise between the SST and the separated model. And for this case, also the same conclusion can be drawn as the blended model tried to eliminate the effects of the jet model and only use the features of the SST model and the separated model to build a good approximation of our solution by using the blending approach. So that's it for me. Thank you very much. If you have any questions, feel free to ask.
Thank you very much for your talk. That's really interesting, also brief and concise.
Thank you very much.
Any question from your part? Otherwise, I will start. Okay, please.
Thank you very much for your talk. It was quite impressive, I would say. So, if I understood correctly, you trained a unique blended model for different test cases, right?
Yes.
And then you try also to test, of course, on unseen test cases. I have a curiosity, but just, I mean, a very simple curiosity. There is like a test case that you found complicated for this application in the sense that maybe the aggregation is not working so well in that test case with respect to the others.
Can you please repeat the question because I didn't hear very well?
No, I'm just curious if among the test flow cases that you consider,
Yes.
there was one particularly complicated where maybe the blended model was not performing so well.
Yes, of course. For example, if you take the training case, which is for the jet, it was very difficult for the blended model to. Let me just. Yes, here, for example, for the velocity along the axis, I will be very happy if the blended model result were closer than this results to the jet, because it looks like the blending strategy fails to attract the converged solution best to the jet solution, because here the jet solution is performing much better than the two others. So here we had the problem because this was a training case, but I think the problem here is how the weights were built, because we built the weights. We have made an hypothesis that our weights were built from the horizontal velocities by using the three models. So maybe if we work further on this to prevent any inconsistency on the weights, because we, as you can see here, the weights are calculated externally, okay, and the blending strategy is performed internally. within the Reynolds stress. So maybe this could be an inconsistency that could be improved in the future. But yes, we have some difficulties, and we can see them before test cases. We can see them in training cases.
Okay, thank you. Another curiosity was, did you try to compare your model, so basically this intrusive, say, model, with a blended model that is non-intrusive? So when you basically do the aggregation on the output and that's it, so no equations after the aggregation?
Yes, I see what you mean. We didn't do this comparison, but the idea here is that when we do the external aggregation, we lose the physical consistency of the solution. Okay, so here we say that maybe sometimes the external aggregation may work better in terms of predictions. But for example, the velocity, because we do the spatial aggregation, so the continuity is lost, obviously. So we just say, okay, we can lose in some precision or accuracy, but we gain in the fact that the solutions that the obtained solutions are physically have physical meaning.
Sure.
Yes.
Okay, thank you very much.
Thank you.
Any other curiosity? Okay, I have just a few curiosities and one question. Regarding not the blended model, not the blended models, but the construction of every, let's say, expert, why
Yes.
the pop projection for constructing the weights you have considered only the two invariants? The first,
Because we are in 2D, so we have only two invariants.
Oh.
If we are in 3D, yes, this is a very good question. So let me just precise. When we are in 2D, we have three tensors and two invariants that arise. However, if we are in 3D, we will have 10 tensors and 5 invariants.
yes, that's
Yeah.
the point.
Yes.
So in 2D, the only invariants that matters are the first two, or the other one are zero. I don't remember. Sorry for the question, but
Sorry, can you repeat that, please?
in 2D,
Yes.
the other invariants, others than the first two, are zero or does not matter at all.
They don't matter at all because they don't arise as they don't have a meaning in 2D.
Okay, understood. So thank you. So the second question is regarding the construction of your blended model. Why you have only considered the horizontal velocity for the random forest regressor?
This was a random choice. We could have used the whole vector to construct the weight. We could also use the if we have access to pressure. It was just a choice. This is I recognize that this is not the best way to do it, but this was a choice, and yeah.
Because I think that if you use, for example, vertical velocity, the model will generalize better in the periodic years and other test case outside of the training. I believe, I think. Maybe.
I don't know. I can't say because I can say because you can, for example, build very good weights here, but when you deploy these weights within the Rand's equations, you can have some mismatches. Like you will not. It's not guaranteed that you will obtain the like a very good fit with the data, with the wanted data. This.
Related to this question, what do you think training online in an online fashion. I mean, you must follow it in order to be consistent with the offline training.
Yes.
You to construct your model upon your discretized equation.
Exactly.
So why? In your opinion, should a differentiable framework help your training?
Yes, that will be the best thing to do. We didn't do it, but this is the best thing to do, I
So
believe.
it's a really good research direction in this context.
Exactly, yes. Learning the corrections online is the best way to do it, but it's not straightforward to do it. So we go step by step.
I know.
Yeah.
So, regarding another curiosity related to the mapping eta from the flow features to the weights.
Yes.
In your experience, you have used all the 11 flow features that you have mentioned, right?
Yes.
That were used in a paper of Ling and template Ling something. I'm not sure that.
Yes.
Have you tried to discard some of the features and let's say create a sort of classification of what are the best features to use in order to construct your model? If yes, what are the best that are convenient to use?
This is also a very good question because first of all, the set of features that we have used have many problems. The first problem is the normalization, as you can see here, because sometimes this normalization fades the physical meaning of the feature. Okay, so yes, we need a very good choice of features. I didn't personally, I didn't did this study to select the best feature, but before that, what I think we should do before is to first get rid of this normalization because it's not that good as we have observed. Okay, and once we do that, we can then use techniques to select the best features that are relevant, that gives the best even for the best to give the best learning of the features weights mapping, or even in doing clustering because we have some problems also with these features doing clustering in flows. So yes, this is a very interesting question and a good direction to refine this features question. It's not a closed question yet, but there are some attempts that we are trying to do.
Thank you very much. So
Thank you.
yes, and let's say that there is a room of improvement for this work.
Yes.
Yes, but yes, okay, that's really cool. So, any other question? So from online? Let's thanks again, Mourad.
Thank you very much.
Well, thank you. Let me. Okay, thank you, Mourad. We have finished.